Welcome back. In this video, we're going to get into the details or specifics of how correlational research is done. We're going to talk about the two major types of correlations. I'll define them and I'll provide at least a few examples of each. After that, we'll talk about the two features of a correlation that can be seen in a set of data. And then we'll talk about how a person takes a set of data and measures those features of the correlation. So the two major types of correlations are a positive correlation and a negative correlation. I mentioned earlier that a correlation is a tendency for two things to go along with each other. It's a tendency for two things to go hand in hand. And it turns out that there's not just one type of correlation. There's actually two types, or two major types. And a positive correlation is a direct relationship between two variables. So a positive correlation is a tendency for two things to go up together and down together. When two variables have a positive correlation, it means that when one variable increases, the other one tends to increase as well. And when one variable decreases, the other variable tends to decrease as well. And so basically, when one variable is low, the other tends to be low. When one variable is high, the other tends to be high. And one example of a positive correlation is commute time and commute distance. When a person's commute distance goes up, the person's commute time will typically go up. And when a person's commute distance goes down, the person's commute time will typically go down. Those two variables go up and down together. Another example of a positive correlation is the amount of time a person spends in school or in college and the amount of money the person spends on tuition. So a person who spends 1 year in college will typically spend less in tuition, and a person who spends 5 years in college will typically spend more on tuition. And a person who spends 10 years in college will typically spend even more in tuition. So when years in college goes up, amount of money spent on tuition typically goes up along with it. Now, a person's years in college can't go down because once a person spends a certain number of years in college, the person can't delete or erase those years. But if a person could bring the number of years in college down, then the tuition expense would go down with it. So basically, it's not possible for number of years in college to actually decrease, but if it could decrease, tuition expense would decrease down with it. Another example is the amount of time it takes a person to vacuum his or her home and the amount of time it takes a person to dust his or her home. A person who lives in a small house will not have to spend much time vacuuming or much time dusting because there isn't much area to cover. And when a person lives in a large home, the person will have to spend more time vacuuming and more time dusting because there's more area to cover. So when the size of the house, when the size of the home increases, time to vacuum and time to dust both increase, and they increase together. And when the size of the home goes down, time to vacuum and time to dust both decrease. So vacuum time and dusting time increase together and decrease together depending on the size of the home. And I wanted to include that example because I wanted to provide one example, or at least one example of a correlation in which it's not a cause and effect relationship. The first two examples I provided were cause and effect relationships because when commute distance goes up, that causes commute time to go up. And when years in college goes up, that causes tuition expense to go up. But my third example, the correlation between vacuum time and dusting time, is actually not a cause and effect relationship. It's actually a correlation that's driven by a third variable. So in that case, in that example, when the third variable, the home size, changes, it causes the other two variables to change along with it. So what I'm really getting at here is a correlation can either be a cause and effect relationship in which A leads to B, or it can be a correlation driven by a third variable in which variable C, a third variable, leads to both A and B. And The second type of correlation I just described actually has a specific name that I will get to later. But I'm not going to tell you right now because I don't want to give out too many terms all at once. So now, moving on to a negative correlation. So I provided three examples of positive correlations, and moving on to a negative correlation. A negative correlation is an inverse relationship between two variables. A negative correlation is when one variable rises and the other variable tends to decrease. So when two variables have a negative correlation, it means that the two variables tend to move in opposite directions. When one variable increases, the other variable tends to decrease. One example of a negative correlation is number of responsibilities and amount of free time. When a person's number of responsibilities goes up, the person's free time will typically go down. And so those move in opposite directions, like these two arrows you see right here. Another example of a negative correlation is age and years until retirement. When age goes up, years to left till retirement will typically go down. Because, for example, a 20-year-old typically has 45 years left until retirement, but a 30-year-old only has 35 years left. So yeah, when one variable goes up, the other tends to go down. Another example of a negative correlation might be amount of money spent on takeout per month and amount of money spent on groceries per month. When a person's amount of money spent on takeout goes up, the person's grocery expense will typically go down. So yeah, those are just three examples of negative correlations. And these terms, direct and inverse relationship, are more casual terms that tend to be used more often in everyday life. That's why I included them to help you connect them to these new terms, positive and negative correlation, which are more statistical terms. And you might be wondering, why do people call them a positive and a negative correlation in statistics? Why don't people just call them direct and inverse? Like, where are these names, positive and negative, coming from? And I wanted to give you a couple of different reasons why people use these terms, negative and positive. First of all, when you plot a positive correlation in a graph, the line rises from left to right. It has a positive slope. And when you graph a negative correlation, the line decreases from left to right. It has a negative slope. Also, if you calculate a statistic called a correlation coefficient, which we'll get to later, to measure a correlation in a data set, the correlation coefficient comes out to a positive number when the two variables have a positive correlation, and it comes out to a negative number when the two variables have a negative correlation. So that's one other reason why these terms positive and negative are used. So I just want to help you get an idea of where these words positive and negative are coming from. So now let's move ahead and talk about the two features of a correlation in a set of data. Before I move on, I wanted to quickly go back to what I was saying about how a correlation is a tendency for two things to go along with each other, or hand in hand. You can think of a positive correlation as a tendency for more of one thing to go along with more of something else. And you can think of a negative correlation as more of one thing going along with less of something else. So I just wanted to help you connect these two types of correlations to how I was describing correlation earlier. So now let's move ahead and talk about the two features of a correlation. The two features of a correlation are its direction and its strength. The direction of a correlation is pretty straightforward because we just talked about the meaning of a positive and a negative correlation, and the direction of a correlation is just whether the correlation is positive or negative. A correlation can go in the positive direction or it can go in the negative direction. The strength of a correlation is the consistency of the relationship between the two variables. So a stronger correlation is just a more consistent relationship. It's a relationship that holds true more often. A strong correlation is a correlation that holds true most of the time or even all of the time, and a weak correlation is a correlation that holds true some of the time but not as consistently. When a correlation is weak, there are more exceptions to the rule. So let me just give one example of a strong correlation and one example of a weak correlation. So an example of a strong correlation would be commute time and commute distance. When a person's commute distance goes up, the person's commute time will typically always go up, at least a little bit. And when a person's commute distance goes down, the person's commute time will typically always go down. Now, there are some exceptions because traffic does matter. And also, a person might change his or her mode of transportation. For example, if a person moves further away from work or school, the person might decide to take a train instead of driving. But the correlation is still pretty consistent because if a person moves, let's say, 50 miles further away from school, that person's commute time is probably going to go up. And when a person moves 50 miles closer to school, that person's commute time is probably going to go down. That's pretty consistent. An example of a weaker correlation might be income and account balance. When a person's income goes up, a person's account balance will go up some of the time, and when a person's income goes down, the person's account balance will go down some of the time. So there is, in general, on average, there is a tendency for a higher income to go along with a higher account balance, and for a lower income to go along with a lower account balance. But that correlation is a lot less consistent because it depends on certain factors. It depends on how much a person is spending per month. If a person has a high income and the person is spending a lot of money paying off bills, or let's say paying off student loans, that person might still have a low account balance. So that correlation is less consistent. It holds true some of the time, but it's not as consistent as the correlation between commute time and commute distance. So now let's move ahead and talk about how a person can measure two variables and actually determine the direction and strength of the correlation within the set of data that was gathered. All the examples of correlations I've provided so far are familiar examples from everyday life, but in a correlational study in psychology, you can't predict with 100% certainty what the direction and strength of the correlation will be. And you have to gather a set of data and then use that data to determine the the direction and strength of the correlation within your set of data. So for example, let's imagine that I'm doing a correlational study and I'm measuring, let's say, income and happiness. I don't know, I'm not 100% sure what the direction and strength of the correlation will be between income and happiness among my participants. It might turn out to be a positive correlation in which the people who are earning more will tend to be happier, or it might be a negative correlation in which the people who are earning less tend to be happier. And I also don't know exactly how strong the correlation will be. It might turn out to be a highly consistent relationship, or it might turn out to be a weaker relationship in which there are a lot of exceptions and a lot of variability. So in that case, I would have to look at my data before making any conclusions. And now what I'm going to tell you is how to take a set of data and actually measure the strength and direction of the correlation within this set of data so that a conclusion can be reached based on evidence and not just common sense or intuition. So there are actually two ways to determine the strength and direction of a correlation within a set of data. You can create a scatter plot, which is a certain type of graph, or you can calculate a statistic called a correlation coefficient, which actually measures the strength and direction of a correlation within a set of data. And first, let's talk about how to determine strength and direction using a scatter plot. So I haven't actually shown you how to create a scatter plot, but if you've taken a stats class before, you are probably familiar with it. It's when you In a scatter plot, you plot a bunch of points, and each point has a value on both the x-axis and the y-axis. So, for example, imagine I ask 20 people, how old are you, and how many birthdays have you celebrated during your lifetime? Each person would be one dot on this graph because each person's dot would represent both their age and their number of birthdays. For example, a person who's 1 year old and has celebrated one birthday would be at one on the x-axis and one on the y-axis, and they would be right here at the bottom corner. A person who's 20 and has celebrated 20 birthdays would be at 20 on the x-axis and 20 over here on the y-axis. So 20 and 20, and they would be out here further up in this area. So, and also in a scatter plot, you can create a line like this that shows the overall trend in the scatter plot. So if the line is rising like this, it just means that the overall the dots are moving upward from left to right. And if the line is dropping over here, it means that the dots are overall decreasing from left to right. It means they're moving downward from left to right and hugging this line. So if you want to use a scatter plot to determine the direction of a correlation, the rule is pretty simple or straightforward. If when the line rises, it means that the correlation is positive. When the line decreases from left to right, the correlation is negative, and when the line is flat, there's no correlation. So an example of a positive correlation would be, or the example I have here is age and number of birthdays. Typically, as a person gets older, they're celebrating more and more birthdays. So as age goes up, number of birthdays goes up, and you get a rising slope. Hours awake and hours asleep is a negative correlation because if a person starts to spend more and more time awake per day, the person is spending less and less time asleep per day. So as hours awake increases from left to right across the x-axis, hours asleep goes down. So notice how hours asleep is going downhill as hours awake increases from left to right. That's a negative correlation. And I was, just based on my intuition, I was thinking that there is probably no relationship between shoe size and number of vacations planned, because those two things don't seem to have anything to do with each other. But like I said, common sense and intuition can be wrong, so there might actually be a correlation between shoe size and number of vacations planned. But I just had to think of some example of something that might have no correlation, and this is what I came up with as my example. So what my intuition was telling me was that overall, people, or on average, people with lower shoe sizes and people with bigger shoe sizes are about equal in terms of how many vacations they're planning. So if you looked at people with small shoe sizes, you would see a range of number of vacations being planned. And if you looked at people with large shoe sizes, you would see a similar range of number of vacations planned. But overall, there'd be no difference between the people with the smaller feet and the people with the bigger feet. That's my intuition, I guess. So this is how you determine direction using a scatter plot. Now let's talk about how to determine strength using a scatter plot. So now we're talking about how to determine the strength of a correlation using a scatter plot. If the line is flat, there's no trend, then there's no correlation at all. And it doesn't depend how closely the dots are hugging the line. So this graph right here and this graph right here would both be no correlation because in both cases the dots are staying level from left to right. They're not rising or going down. Now, if the line does have a slope to it, then the correlation, or if the line is not completely flat, then the strength of the correlation depends on how closely the dots are hugging the line. So here we have a line that's rising, and the line is rising because in general the dots are moving up from left to right. Notice how this range of dots here is somewhat lower than this range of dots at the right end. But so it is a positive correlation. It is trending upward. But notice how the dots are overall pretty spread out from the line. They're not hugging the line very closely. Since the dots are spread out so far away from the line, it's a weak positive correlation. Over here, the dots are hugging the line much more closely, which makes it a stronger positive correlation. And over here, the dots are trending downward in general, but the dots aren't hugging the line very closely, so it's a weak negative. And over here, the dots are trending downward, and the dots are hugging the line closely, which makes it a strong negative. So overall, if there's no trend and the line is flat, there's no correlation. It doesn't, the closeness of the dots to the line doesn't matter. If the line is diagonal, then the strength of the correlation depends on how closely the dots are hugging the line. So to summarize, overall, the if you want to use a scatter plot to determine the direction and strength of a correlation, the direction depends on which way the line is going. If the line is rising, it's a positive correlation. If the line is going down, it's a negative correlation. And if the line is flat, it's no correlation. If you're determining strength based on a scatter plot, it's if the line is flat, there's no correlation. And if the line is diagonal, the strength depends on how closely the dots are hugging the line. And now we're going to move ahead and talk about how to determine the direction and strength of a correlation using the correlation coefficient, which is a statistic that actually measures the strength, the direction and strength of a correlation in a data set. Let's now talk about how to determine the strength and direction of a correlation using the correlation coefficient. So I said that the correlation coefficient is a statistic. It has a formula, and we're not going to cover the formula in this video. We're just going to cover how to interpret the correlation coefficient. So the direction of the correlation is just the sign of the correlation coefficient, and the strength is the distance from zero. So in other words, if the correlation coefficient comes out to a negative number, then the correlation is negative in that set of data. If the correlation coefficient comes out to a positive number, the correlation is positive. And if the correlation comes out to zero, it's no correlation. And a correlation coefficient further from zero in either direction indicates a stronger correlation. So for example, going in the positive direction, 0.5 is stronger than 0.2, and 0.2 is stronger than 0.1. Going in the negative direction, negative 0.5 is stronger than negative 0.2, and negative 0.2 is stronger than negative 0.1. So as you move out toward plus 1, if you start at 0 and you move out toward plus 1, you're moving toward stronger correlations. And if you start at 0 and move out toward negative 1, you're moving toward stronger correlations. But so if I asked you what correlation is stronger, negative 0.9 or positive 0.2, you would say negative 0.9 because negative 0.9 is much further from 0. It's way out here, and positive 0.2 is just pretty close to 0. So I think what sometimes causes students to get stuck on this is that they think that a positive correlation is always stronger than a negative correlation. So, but that's not the case. A positive correlation can actually be weaker, and a negative correlation can be stronger depending on which one is further from 0. And I also included a few images here just to show you what some different correlation coefficients might look like in a scatter plot. So a correlation of 0 might look something like this. So if you took this graph right here, this set of data, and actually calculated the correlation coefficient, it would come out to zero because it has no trend. And if you took this data right here and calculated the correlation coefficient, um, I'm guessing it might come out to about negative 0.5, but I'm not completely sure because I'm not that good of an artist. I'm not that good at drawing these. I'm not that good at drawing a correlation, a scatter plot for a particular correlation coefficient. So don't hold me to it. But this one is probably about 0.5. If you took this set of data and calculated the correlation coefficient, it would probably come out to about 0.5, but once again, don't hold me to that because this isn't meant to be a precise drawing. It's just a rough estimate of what a 0.5 might look like. And if you um, if you have a graph in which every dot is on the line, then you have a correlation coefficient of -1. And if you have a graph in which every dot is on a rising line like this, you have a +1. And this data set here at the left end is called a perfect negative correlation, and this data set at the right end is called a perfect positive correlation. So notice how a negative correlation can't get any stronger than this, because if the dots are all perfectly on the line, the dots can't hug the line any more than that. And notice how a positive correlation can't get any stronger than this. If the dots are all hugging this rising line perfectly, you can't get any stronger than that. Because remember, I said strength is how closely the dots are hugging the line. So a correlation coefficient has to come out to a number between -1 and +1. And if it's a -1, it's like this graph at the left end. And if it's a +1, it's like this graph at the right end. And I just want to share a couple examples of perfect correlations. It's very hard to think of an example of a perfect correlation because they aren't very common, at least, especially not in psychology or social science, because things tend to vary. You tend to have variability in social sciences. But an example of a perfect negative correlation is hours awake and hours asleep, because when your hours awake goes up by 1, your hours asleep always goes down by 1, and every dot is on this line going downward. There are no exceptions. You can't have a person down in this corner who's, let's say, awake 2 hours per day and also sleeping 2 hours per day. You just don't have those exceptions. A person who's awake 16 hours is always sleeping 8 hours. A person who's awake 17 hours is always sleeping 7 hours, and so on. At this right end, an example of a perfect positive correlation would be age and the total number of birthdays a person has had in his or her lifetime, because when your age goes up by 1, your number of birthdays always goes up by 1. So if you're 1 year old, you've had 1 birthday. If you're 2, you've had 2 birthdays. If you're 3, you've had 3 birthdays. And every dot has to be on the line. And all of the correlations that we see in psychology would fall in between -1 and +1, because in psychology, there's variability, and you don't just have a rule that's always followed 100% of the time. You always have outliers and people who are exceptions to the pattern. And before I wrap this up, I just wanted to mention a couple quick points. So right here in the middle, I have a square or rectangle looking shape as a correlation of 0. And a correlation of 0 doesn't have to look exactly like this. There just has to be no overall trend from left to right. So I could have drawn just a blob looking shape, like a circle or an oval, and that would be 0 because it would still be not rising or falling from left to right. And one thing that I also mentioned in the type lecture is if a scatter plot has a U shape, that's also a correlation coefficient of 0. So I could have drawn a U-shape for 0 if I wanted to. And that's because when you have a U-shaped scatter plot, the left half is a negative correlation, and the right half is a positive correlation, and the two sides cancel out, and it makes a correlation of 0. Also, an upside down U-shape is a correlation of 0 because if it's an upside down U-shape, the left half is positive and the right half is negative, and the two sides cancel out and make 0. And one other point I wanted to mention is I also want to mention that the strength of a correlation doesn't depend on how steep the line is. If the line gets steeper, that doesn't make the correlation stronger. The correlation only gets stronger if the dots move in closer to the line. So you actually could have a line with a very shallow slope and have a strong correlation if the dots are hugging the line closely. Now, if the line is completely flat, there's no correlation at all. It's a correlation of 0. But you could have a graph where the line has a very shallow slope, and it's still a strong correlation because the dots are just hugging it very closely. And you could also have a graph with a very steep line and have it be a weak correlation if the dots are far away from that line. So when you think of the strength, think of how closely the dots are hugging the line and not how steep the line is. And finally, as my last point, I wanted to mention that the correlation coefficient and the scatter plot are complementary. They go along well together because they make up for each other's weaknesses. The correlation coefficient gives you a precise measurement of the strength of the correlation, and the scatter plot gives you a visual image of what the data looks like, and it allows you to see what the data looks like in more detail. So they do go hand in hand pretty well. Unfortunately, in a psychology article, you only see correlation coefficients, and you rarely, if ever, see a scatter plot. And that's because in a typical correlational study, lots of correlation coefficients are calculated, not just one correlation coefficient. And it's not practical to include several, it's not practical to include several different scatter plots all in the same article if, let's say, 20 different correlations are being calculated, because if you tried to put 20 scatter plots in an article, it would just take up lots of space. So yeah, that's the all I had to share for this topic. So we've covered all of the specifics of correlational, well, we've covered most of the specifics of correlational research that I wanted to cover. And in the next, in the next video, I'll talk about so at this point, we've covered most of the specifics and details of correlational research that I want to cover. In the next video, I'll give a step-by-step example of creating a scatter plot, and then in the next video after that, I'll talk about why a correlational study is low in internal validity and doesn't lead to a confident cause and effect conclusion. And then after that, we'll be finished with this topic of correlational research.